6. So this is about positive test with 2,4-DNPH. So 2,4-DNPH will give you an orange PPT, not just with any carbonyls, only with ketones or aldehydes, not carboxylic acid. Okay, so not carboxylic acid, not esters, which means, well, you only have option A, okay, because S is a carboxylic acid and T is an ester. Okay. Question 27, what do we have? Okay, so we are told that this carbon and then C4H9, Cn and the OH and the CH3 come from HCN plus a carbonyl compound X. Okay, what is important is you notice the OH and the Cn is on the same carbon. This is called a cyanohydride. This is a case study. This is from AS chemistry under ketones and aldehyde chemistry as part of the nucleophilic addition mechanism. Okay, you can add carbons using nitrile, using Cn minus, but this reaction is also catalyzed by NaCN, as well as you have to do it cold around 15 to 20 degrees Celsius because the HCN can vaporize easily. So this mechanism is definitely nucleophilic addition. But what is important is you could hopefully see that the other two groups, which I'm circling in green here, so it's going to be a carbon, C4H9, and then CH3, like that. So it has to be a ketone and not an aldehyde, which means we are looking at option D. Option D is the correct answer. Okay, let me just spend a few minutes on this mechanism. So we are catalyzed by NaCN because this is Na plus Cn minus, whereas this is a molecule. So the better nucleophile is going to be the ionic form from the catalyst. Rich attack the poor, and then you kick out the electrons to the oxygen. So what happens is C4H9, and then you get a CH3, you get an O minus, and you have the Cn like that. So the bond is between carbon and carbon, not between carbon and nitrogen, yeah? What you have then is you have HCN molecule, which is polar, but it's not ionic. But then now you can break it, and you can form this product, which is carbon C4H9. I'm just moving things around because these are all single bonds. In a three-dimensional setting, you can definitely just move things around. And that is just a CH3, which is as portrayed in the question. And what happened very importantly is you kick out and you give out the electrons to the carbon. That means this is regenerated or reformed. After all the HCN has been consumed, because it's a reactant, you will always kick out one Cn minus, which regenerate the catalyst, because the catalyst is never used up in the reactions. They only get involved, but they never get used up in the reactions. Question 28, what do we have here? Okay, so Y is just treated with a single reagent and you get 2-methyl-butanoic acid. So from the name itself, you should be able to draw a carboxylic acid, a 4-carbon carboxylic acid. So there is 1, 2, 3, and 4, and there is a methyl group, a CH3 at position 2. Now what could be that product there? So altogether here, hopefully you can see there are 5 carbon total. Okay, pentane 2-on. So what do we have? A is pentane 2-on. So it's a ketone. But here you can see 1, 2, 3, 4, 5 carbon straight chain. You compare that with the 4 carbon straight chain in the question given. So it's impossible to get it one step, one single reagent from A. Okay. Option B, 2-methyl-butane 2-on. So I'll draw, because it is a butane 2-on. So I have to draw the branch, 1, 2, 3, 4, butane 2-on. Butane, 4 carbons, butane 2-on, OH at position 2. I have a methyl group there. To get a carboxylic acid at this alcohol, you can't even oxidize this alcohol because the carbon with the OH is bonded to 1, 2, and 3. This is a tertiary alcohol, can't be oxidized at all, okay? Because you don't have any hydrogen on this carbon with the OH to be lost. So how can you oxidize it? Option C, so C and D looks more like the right answer because it's to do with nitrile. All right, so butane nitrile, 1, 2, 3, 4. And then I have 1, 2, 3, and 4. I have a 2-methyl butane nitrile. Nitrile, 4 carbon, including the nitrile carbon being the most important one, 2-methyl. I can do acid hydrolysis, dilute HCl, and reflux. What I get is I will get a carboxylic acid there, which is 2-methyl butanoic acid. So C is going to be our answer. Okay, so there is acid hydrolysis of esters, which is part of AS chemistry. On the other hand, if you have propane nitrile, 1, 2, and 3, and you have methyl propane nitrile, so they don't say 2, but there's the only place you can put it if you want it to be 3 carbons, which is brunch. All right, well, I can tell you that it's definitely wrong because 4 carbon total. 4 carbon total, even when you hydrolyze it, you are still going to get 4 carbon total, which is not the same as the butanoic acid. This is actually 1, 2, and 3. This is 2-methyl propanoic acid because it's 3 carbon carboxylic acid. D is definitely wrong. Question 29. What do we have? Okay, well, let's have a look. So I'm just going to convert that into skeletal. So there's a carboxylic acid. LiAlH4 can reduce our carboxylic acids all the way to the primary alcohol. So this is P. The carbon with the OH is bonded to one other carbon. So this must be a primary alcohol. So that means C and D is out. And now I draw the other one. This is an ester. What else? There's an ester. And then I'm doing hydrolysis, whereas previously I was doing reductions because LiAlH4 is my reducing agent, very, very powerful reducing agent. This is my ester, so ester can get hydrolyzed there, and that bit will give me my carboxylic acid, whereas the other bit will give me my alcohol bit. Okay, so they don't tell us what condition. I shall assume it to be acid hydrolysis, but of course if it is base hydrolysis, you get a salt instead of the acid itself. Now the carbon with the OH is bonded to 2 other carbons. This has got to be a secondary alcohol because the carbon with the OH is bonded to 2 other carbons. Well, this is a carboxylic acid, ethanoic acid. This is going to be R, but the only thing they ask is so the first one is primary, the second one is secondary, primary and secondary. So there's option B as the correct answer there. Question 30. So this is about infrared. So the last question in this section A. First of all, I can see no broad strong absorption at around 3000 to 3500. So it's absent. It's absent. Okay, if it is absent, that means no OH, because you would expect this to be very distinguishable, which means if there is no OH, I can immediately cross out A, I can immediately cross out B because they have got the hydroxyl OH. I'm left between C and D. If you look at C and D, so option C and D, the other thing I should be looking for is no strong, sharp absorption at around 1800 or 1700 to 1800 wave number. So again, it is absent, it's not present, so there's no carbon oxygen carbonyl of ketone, aldehyde, acyl chloride, I don't know, ester, amide, whatever carbon oxygen bond. You don't have that carbon oxygen double bond, so therefore I can cross out option D. So D is definitely out. So therefore we're just looking at option oops, sorry, what I meant was I can cross out option C because option C has got a carbonyl aldehyde at the end there. So option D is going to be my answer there. Okay, moving on to the last 10 questions, which are the section B type of questions. So we know in the section B we have 4 statements. We have A, B, C, and D. So there's 1, 2, and 3 are correct. There's 1 and 2 are correct. There's 2 and 3 are correct, and only 1 is correct. So by logic, by default, our logic is to check for statement number 2 first, because if statement number 2 is wrong, that means only D can be the answer. But if number 2 is correct, we have to go for number 1 and then number 3 in that particular order, unless they are specifically like number 1 or number 3 that you can have a look at it, and then like you read through it, you see it, and you could see something is wrong already. Okay, anyway, so jumping straight on to question 31. This is about first ionization energy. So they're asking on first ionization energy, what is correct about the first ionization energy. If I check for number 2, they say they decrease down group 2. That is actually correct, because going down the group, you have more shells, and as you have more shells, the valence electrons are way more shielded by the inner electrons, and if they are way more shielded, therefore slightly easier to remove, as we are talking about the effective nuclear charge. Effective nuclear charge is basically the net electrostatic force attraction between the valence electrons and the positive charge in the nucleus, basically the nuclear charge, taking into account the shielding effect as well, which of course gets stronger and stronger as you have more and more shells down group 2. So number 2 is definitely correct. Going straight to statement number 1, they say they are always endothermic. By default, if you think about the definition of first ionization energy, so there's X, gas, going to X plus gas plus electrons. I never really define it by memory. I define it in terms of the equations, including the stat symbols. This is very important. So it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form or to produce 1 mole of gaseous ions with a single positive charge. So that is essentially as complete as it could be, and I know all of that because I'm just putting the equation into words. So there are many things that you don't have to memorize word by word, and if you have done that, you probably have been learning chemistry the wrong way. Okay, now they say statement number 3, they say they decrease across period. So period 3 is your case study. So in general, we know that ionization energy definitely increase. So I know that statement number 3 is definitely wrong already. But obviously, I'm just going to show you what is happening. So there will be a slight drop when you go to the p subshell. And there's a second slight drop when you have the paired electron repulsion. And then it go all the way down there. So sodium, and then magnesium, and then aluminium. And then this is between the S to the P. So the 3S to the 3P. So the electrons in the 3P are slightly more shielded, and the valence electron is slightly more shielded, and therefore slightly easier to remove compared to the valence electron in the S subshell. For this second drop is to do with the P3 versus the P4. That is basically to do with the paired electron repulsion. So when you have 4 electrons in the p orbital, we said that this thing, the paired electrons repel more. If the paired electron repel more than the unpaired electrons, such as for the 3p3 configurations, so obviously we are removing something which is unfavorable, so slightly easier to remove something which is unfavorable, and therefore you get a second slight drop in your first ionization energy. And there's going to be between group 15 and group 16, so there's between phosphorus and sulfur. Okay, so be very careful. It's not between group 13 and 14, it's between group 15 and 16, because these are p orbitals which can fit up to 6 electrons. That's basically the right hand side of the periodic table, where you're already broken off from the S subshell there. And then it goes to the highest value when it reaches the noble gas, and then obviously when you need to fill in a new shell, the new shell is further away, more shielded valence electrons, and therefore a lot lower than argon, and obviously lower than sodium because we are going down the group. So when you say it decreases across period 3, we know that that is absolutely wrong. In general, it increases, but there are 2 small drops. Okay, so only 1 and 2 are correct, so that means there's option B there. Question 32, so this looks like this is, what is this? Okay, never mind. So let me just have a look at this. Okay, I think it's important that I write down the equation because there's something to be discussed here. Yeah, I mean the number in front of the species basically tells you how many of it you are forming. If I check number 2 and number 1 is to do with oxidation and reduction. If we want to think about oxidation number, we don't care about the number in front, we just take at one formula unit, which is CrO43 minus. Minus 3 is the overall charge of the ion, so it's the oxidation number of the ion. Chromium is what I want to find. There are 4 oxygen, each of which is minus 2. The common oxidation state of oxygen when it's bonded to something else, due to its highly electronegative nature, it's bound to be minus 2. Unless it's a peroxide, then it's minus 1. Unless it is bonded to itself in an element, then it's 0 oxidation number. There's minus 3 plus 8. There's chromium plus 5, which is quite uncommon. And what we have here is CrO42 minus, because I'm just looking at one formula unit in order to get the oxidation number. So 4 oxygen, so 4 times minus 2. So there's minus 2 plus 8. There's chromium plus 6 there. This is chromium 3 plus on its own, so very straightforward. There's chromium plus 3. This is a classic disproportionation reaction. So disproportionation reactions refer to a redox reaction where a species is both oxidized. So this is an increase in oxidation number, so it's oxidation. And also it is also reduced in the same reaction where the oxidation number decreases from plus 5 to plus 3. Okay. Anyway, so now what can we say? 2 of it goes to 2 of that, so we can see that 2 of that actually get oxidized. So 2 of CrO43 minus, but then only 1 of the CrO43 minus get reduced. As you could see, that is essentially what is correct, because 3 mole of it, 2 of it is used for oxidation, 1 of it is used for reduction. Changes in oxidation number must be balanced. If I write in pink, plus 5 to plus 6 is increase of 1, and then plus 5 to plus 3 is a decrease of 2. Changes in oxidation number must be balanced in a redox equation. This is stated in the AS redox topic, I think the very last bit of your syllabus, using changes in oxidation number to help balance chemical equation. So that's multiplied by 2, that's multiplied by 1. This is how many. So obviously you can see 2 of that CrO43 minus get oxidized and 1 of it get reduced. So number, what is that? That is number 1, that is correct. There is number 2, that is about the oxidation, that's also correct. How about number 3? It says 3 moles of electrons are transferred. 3 moles of electrons are transferred. We need to be very careful here. This is to do with losing 1 electrons, but there are 2 electrons lost altogether because 2 of that species, each of which lose 1 electron. You have 1 of that species gaining 2 electrons, so total only 2 electrons transferred. 2 mole of electrons get transferred. Something lose 2 electrons total, something gain 2 electrons total, so it's not 3 mole, which means which means statement number 3 is actually wrong. So only 1 and 2 are correct. And again, so that is option B. Only 1 and 2 are correct. Question 33. This looks like a biochem kind of thing. What do we know? Slightly acidic reaction is very slow, but then you add in a biological catalyst and the reaction is much faster for lactose but very slow for sucrose. So catalyst is very specific, obviously. So catalyst, especially enzymes. So we're talking about biological catalysts. So enzyme have something called active sites. If you have done O-level or IGCSE biology, you will have known this. This active site involve a lock and key mechanism. So only something of the right size can fit into the active site, and therefore the catalyst is very specific to the substrate, basically the disaccharides in this case. Therefore it's very, very specific. Okay, so this is statement number 2, which is definitely correct. These are all part of the enzyme catalysis essay in an A2 rate of reaction setting. In a paper 4 for the 9701, it's usually worth 3 or 4 marks kind of essay. So it's important that you understand the concept here, all right? Now, it says in statement 1, the catalyst increase activation energy. Okay, I can tell you the catalyst is supposed to speed up the rate of reaction, right? Okay, so catalyst is supposed to speed up rate of reaction. Okay, so how do they speed up rate of reaction? They have alternative reaction pathway. They provide alternative reaction pathway with a new lower activation energy. So the original pathway is still there with the same activation energy, which is a bit higher, but there's the whole idea of using a catalyst, whether it's biological catalyst or just a normal inorganic catalyst. They are going to give you this alternative reaction pathway. This choice has a new lower activation energy that will help to make the reaction faster. As a result of that, I can tell you that statement number 1 is definitely wrong, because it's saying the catalyst increases the activation energy. The increases is definitely something which you don't see happening with a catalyst, especially the statement in the question itself, the description given. It says that it remains slow for sucrose, because it's not specific for sucrose and maltose, but it's much faster for lactose, because lactose probably could fit into the active site. But for lactose, essentially, the alternative reaction pathway has a new lower activation energy, so it doesn't get increased at all. Number 2 is correct. Number 1 is wrong. Therefore, we are looking at C, option C, which is 2 and 3. Okay, so that is without even checking statement number 3. And of course, because what I have said, with lactose is faster, and therefore there must be a different mechanism as a result of this alternative reaction pathway, as opposed to this uncatalyzed reaction, which would be a bit slower without that alternative reaction pathway. Okay. Question 34. So this looks like a part of environmental chemistry. I think nitrogen and sulfur, environmental chemistry. What do we have? We have element X, which is a solid under room conditions. Well, we know that there's N2 and we know there's S8. This is a solid at room temperature and pressure. This is a gas at room temperature and pressure. I can safely assume that X is going to be sulfur, I think. Not necessarily, because I think we could also imagine that it could be carbon as well, because they mentioned something about fossil fuels. So carbon is going to be graphite or diamond. I assume we don't want to be talking about diamond. We'll probably be talking about graphite. So this is a solid at room temperature and pressure. It occurs as a contaminant of fossil fuels. Now I can be sure it's a sulfur, because we talk about sulfur contaminated fossil fuels as stated in the syllabus under the sources of sulfur dioxide. So fossil fuels obviously don't contain sulfur, but they can get contaminated with it, and this is a source of sulfur dioxide, which is man-made. And when you burn fossil fuels in power stations, and these fossil fuels contain sulfur as a contaminant, that's how you get SO2 produced as a result of man-made action. Obviously, the natural source of SO2 comes from volcanic eruptions, but sometimes they are specifically for man-made or human source of this sulfur dioxide. All right. What else? In the atmosphere, Y can be oxidized to Z. So X is sulfur. Sulfur plus oxygen give you SO2, but we know that SO2 doesn't go to SO3 unless if it is human action, then we are talking about the contact process. But then in the upper atmosphere, we are not dealing with high pressure or high temperature or V2O5 catalyst. Instead, what we have is the oxide of nitrogen. The oxide of nitrogen acts as a catalyst, and then it will form the SO3. It's not a reversible reaction because this happened in the upper atmosphere. It's catalyzed by NO2. This is the intermediate. You already now have the SO3 because this get oxidized, this get reduced. So this steals the oxygen away, this loses the oxygen away. This has been oxidized, this has been reduced. What happened with the NO intermediate is they will react with more oxygen in the upper atmosphere to give you that catalyst, because a catalyst is not used up. A catalyst is simply involved in the reaction and it gets regenerated or reformed at the end of the reaction. Obviously, then what happened is forming acid rain is not just straightforward. Well, it is actually straightforward once you reach here, but obviously, you don't get SO3 by burning sulfur and oxygen. That doesn't happen unless you are in contact process that is man-made, or unless you're in the upper atmosphere when it's catalyzed by this NO2. Once you get an SO3 form, then it's just dissolved in this rainwater, and you get this H2SO4, which is actually your component of acid rain. Obviously, yeah, okay. So there's the catalysis there. There's actually a form of homogeneous catalysis. Homogeneous catalyst is defined as a catalyst in the same phase or the same state as the reactant. These are all gases in the upper atmosphere, so obviously it's a homogeneous catalyst. It's an AS terminology under the red topic. So what do we know? We know that this is a catalyzed process, so statement number 2 is correct. Atoms of X, so X is going to be sulfur. If X is sulfur, this is a group 16. I was about to say group 6, but you can also use group 16. And what do we know about group 16? We know just now about group 16 when I talk about paired electron repulsion. It's a P4, so it's the fourth column in the P subshell, so it's got 4 P electrons. These are the paired electrons that repel more than the unpaired electrons in the P3 for the group 15 element. So this one has a paired P electrons. This is statement number 1 being correct. Okay, so 1 and 2 are correct. I haven't checked number 3 yet. So which one is Z? So it says when sulfur burns, you get the oxide, and this is Y. So there is X, and there's Y, and then this is Z. And then what happened is when the SO3 dissolves in water, you get a strong acid. So obviously statement number 3 is correct. So therefore 1, 2, and 3 all are correct. We are looking at option A being the best answer here.